Thanks for coming out and coming to this session. Hopefully, everybody had a good lunch and is excited for some afternoon content. So who am I? Jordan Tigani. I helped start this company called MotherDuck, and I've done a lot of stuff in the analytics space for I guess about 15 years. Believe it or not, this is a toned-down version of what I wear at conferences. That was me at Data Council earlier this year. So kind of what I want to do at this talk is I'm going to talk a lot about database architecture and how clients work and how different things should talk to each other. And really my goal is just to get people to think about the abstractions they're using and the architecture as being something that are materially important to how you do analytics and how you understand data. Who here has used Hadoop? Who here still uses Hadoop? Nobody. So once upon a time, Hadoop was the #1 skill you could have on your resume to get you the highest salary, of job, and now it's basically gone. Anybody have venture an opinion on why Hadoop is no longer around? It's slow, hard to use. I think a lot of people actually feel like it was the missteps by Cloudera and Hortonworks and people who were otherwise working on the Hadoop ecosystem, but I don't think that was it. I think it was just that it was the wrong architecture and the wrong abstraction, and so that's the architecture and abstractions are important. So the architecture that ended up sort of winning out for the most part was the cloud data architecture. And I want to talk about a couple of things that enable that. One is just sort of major changes in how storage system works. So first of all, data, instead of being stored on kind of local disks, was stored in an object store. On one hand, it makes a bunch of things harder. On the one hand, it also makes a bunch of things easier. Things like time travel become easy, but updates become virtually impossible. Point updates become virtually impossible. There's a transition of row stores to column stores. Row stores are great for finding a row, updating a row. Column stores are much better for doing analytics, and so systems are able to hide that behind a service boundary. And then also kind of the migration from shared nothing to shared disk. So if you kind of read the database literature, a lot of the people that building parallel architectures were building and basically, okay, I'm just going to stand up a whole bunch of these, and they're not going to have to share anything amongst them, so they can actually be sort of logically consistent. Actually, Redshift is an example of a shared nothing architecture, but Snowflake and BigQuery were examples of shared disk, and then that separation of storage and compute that was made possible by that actually makes a lot of kind of what we consider the modern data warehouse era possible, and you can scale things out individually. So kind of there are some important features that are less well understood that were required to be built because of the difference in architecture. One of those is, okay, well, you have all these files on disk, and you're writing in object stores. You can't update things, so you have to have some sort of file management system. You have to have metadata management to be able to prune and figure out which files you need for a given query. If you're doing fast updates, column stores are really poor at doing lots and lots of updates because they like to compress together lots of things at once. And so mechanisms had to be built for doing streaming, and then writing those out periodically, and then also storage push down. How do you actually push parts of your queries all the way down to the server? So there's a bunch of things that had to be built. This was just work. We did it at BigQuery. Snowflake did it. But there was sort of a parallel thing going on. And the parallel thing going on was were data lakes. And I think data lakes were tended to be sort of refugees from the Hadoop space. And for a lot of reasons, they were great. Hey, I'm going to throw all of my data in this S3 bucket, and then we can figure out what we're going to do with it later. On the other hand, there's a bunch of problems with data lakes, and some of the problems, including data lakes become very hard to manage. Nobody's governing them, but a lot of these things that actually were the problems with data lakes actually were things that were kind of related to things that were solved on the data warehouse side. So if you can sort of compare those problems to the problems that kind of things that were built on the data warehouse, well, there was no kind of centralized file management. So you kind of had to do all that on your own. Nobody was managing metadata, so like you could have like a Hive metastore, but Hive metastore was very loosely coupled. It was actually locally, so it was easy for things to get out of sync. And then Hive metastore was really not something you'd want to have in the query path. It was very hard. It was almost impossible to do fast updates. You kind of were just, you could do a bunch of appends, and then you could query from a large directory if you were appending new files. But like if you wanted to go back and delete something, you were kind of hosed. So the lakehouse architecture was really an attempt to solve a lot of the problems that were in the data lake. And so they basically solved kind of the file management problem. So when you write to a data lakehouse, and you write to Iceberg or Delta Lake or Hudi, actually somebody is either part of the write or part of the read. Somebody is actually doing the file management. There is a bunch of files on disk that represent metadata, and you can use those to do pruning. Of course, those aren't very fast. Of course, also, you still can't really do fast updates because everything is being stored to S3. You can't really do single point updates or a lot of individual requests. There we go. So and this is sort of back to like sort of getting the right abstraction and so having tables versus files. So files, I think there's this meme going around that okay, well if you have Parquet, you kind of, it doesn't really matter what your query engine is, and I believe that like actually the files are sort of the wrong level of abstraction. Yes, they're nice. It's nice to be able to say, hey, I'm just going to copy this file around. But I think as you see in the lakehouse architecture, like you can't really just operate at the level of files anymore because like in Iceberg, if you make an update, there's going to be a bunch of files up there. Some of those files are no longer going to be valid. And so you can't really just copy directories around or copy a bunch of things around anymore. And like there's issues with transactionality and ACID. But on the other hand, files are simple. But they're also, you don't get great performance. You need to have, if you want to do like adequate pushdowns, figure out exactly which files you need a bunch of cached metadata. So actually operating with tables is a much, much simpler way of actually interacting with your data. So like if you're writing code or you're writing something against data, like rather than having to deal with a Parquet file, it's a lot easier to basically say, I'm going to use this table. And especially as we're increasing the level of abstraction of the clients that are talking to the data, really it's like it's equivalently the same thing. You do have to have a client that knows how to talk to your tables, but kind of in the world where you're dealing with lakehouses, you still have to do that anyway because you really don't want to write your own client for Iceberg or Delta. So one of the ways that I see the data lake, the lakehouse evolving, is a lot of the pieces that they're still missing. They're going to start to add those. For example, a service that like Tabular has added a service for metadata, and I think and Delta as well, so that you can actually go to the service and say, okay, what are the things that are actually live in the table, which is a lot faster and a lot simpler and a lot easier to update than a bunch of files on the table. reading through a proxy. Like, so if you give people physical access to data, then it's really hard to apply strong access controls to that data. Like you can't do column-based access controls if you're giving people access to the file. So adding things like proxies, adding things like streaming buffers, and I think Hudi has actually done some of this. Is like adding streaming buffers so that you can write data out and that data gets written out periodically. The thing is, after you've done this, you basically have built a data warehouse. So the lakehouse is kind of becoming a data warehouse. So instead of dealing with files, you're dealing with tables. Then that lets you kind of handle the streaming store, stuff can get coalesced in the background because you actually need to have a service running, and then you can do strong access management. So that's sort of my prediction. But if you do that, then what do you kind of still have this system where you have the query engine that's calling into your lakehouse, which is now a data warehouse. You have a full-blown data warehouse and a query engine. It turns out there's a bunch of things you can do with this, and this is sort of what we at MotherDuck are calling hybrid execution. So why hybrid? So what are a couple of the things you can do with hybrid execution? One is if you've got a query engine and you've got a data warehouse, well, you can actually have you can run the query engine in your web browser. So super fast, super low latency, user experiences that are literally impossible if everything has to hit the server. You can push workloads down to the end user. You can also sort of do data science without borders. So you can basically say, hey, I don't necessarily care where this data lives. I'm going to do a bunch of stuff locally. I'm going to build up some pandas data frames, or I'm going to operate on stuff on my laptop. But then I need access to data that might be actually quite large and live somewhere else. You can marshal and manage all that stuff yourself, but it's work. It's hard, and I think one of the things that is pretty interesting is that a lot of the times people sort of piecemeal build things that basically database functionality. Hey, I just need to sort. I just need to filter. And then you kind of compose these things together, and you realize that that you're doing them very slowly. And I think that's sort of a lot of data science tooling ends up doing some of that work. Much better to actually push this into a database. Another one is just sort of like if you have a large data set in the cloud and you want to operate on it locally, you can basically do sort of smart local sampling, and you basically pull a bunch of data down, operate on that locally, do everything locally, do all your work locally, but then you can push it to the cloud and do the exact same thing. You can do things like client-side decryption, where you never have your encryption key never leaves the client. So the server can actually operate over data, but let's say I need the decrypted value. Seamlessly, that'll get pulled down and decrypted on the client. You don't have to actually worry about doing any of that on your own. So these are just some examples of stuff that you can do. I think there's a bunch of other interesting things. And so this is what we've built at MotherDuck. And so I have a bunch of sort of technical architecture stuff. I'm going to go through it pretty quickly on how this stuff works. But who's familiar with DuckDB? Right, a lot of people familiar with DuckDB. So DuckDB is an embedded database, sort of like SQLite. You can link it into your current executable, so it's super lightweight, super simple to use. I think it's sort of the ideal for, hey, if you're going to replace files with tables, basically because everybody can just use DuckDB and then use the DuckDB as an API to access your data. But sort of typically, in a database, it's sort of a client-server world. So you send your query to the server and you get a result back. DuckDB, you link that into your process so it never has to leave the process. And sort of a database execution 101, there are basically several steps that your query goes through. It's sort of a pipeline. You parse the query to turn it into syntax tree, and then you bind it, which which methods are actually being called, and mapping things to actual data. Then you optimize it. There's a whole bunch of things that involve in the query optimization, and then you actually execute it. And the reason I go through this will be apparent later. So if I just take the previous slide that I showed with how DuckDB works versus how typical servers work, I'm just sort of expanding that out. So the first way you can start to do hybrid is you basically say, okay, I have DuckDB locally, and I'm going to hook into the parser, and then when we basically we're just going to forward everything to the server, and the server is going to do the actual work, and I get results back. And that's sort of the typical, hey, I send a query to the server, and I get a result back. The problem is if I'm accessing local data, then this doesn't work anymore. So the way to handle local data is, okay, I also hook into the binder, and so I'm going to bind, and then if I look at if these tables are referenced or locally, I can do all the work locally, and if the tables are referenced on the cloud, I can do work in the cloud. That's nice, but of course that doesn't let you actually mix local data and remote data. And so, to handle a mix of local and remote data, you actually hook into the optimizer, and instead of sending a query string to the server, you send a query plan, and we make a cut in the query plan where basically the pieces that need to go into the server. It's a little more complicated than that. I'll get into that a little bit. This is kind of the architecture that MotherDuck has built, and it kind of shows there's a bunch of pieces that you need to build if you want to build a data warehouse or a proper analytics platform versus just having kind of DuckDB in the cloud. Because DuckDB doesn't have any idea of users, it doesn't have any sort of so there's no auth system and global catalog and backups, et cetera. So all these pieces that you end up building when you want to put something in the cloud. I think I'll go quickly over this stuff. So the hybrid query execution. The way it works is we do a cut of the query plan. So if there's DuckDB basically builds these pipelines of operators, and if you think of a join, it ends up joining two pipelines. There's a probe side and a build side. At the interfaces of these pipelines, we insert either uploads or download operations. So you can see what this looks like. So if you run a query where everything is local, this looks like this is the DuckDB query plan. It's just everything is local. It's super simple. You can see this simple join. But when all tables are remote, everything is the same, except at the beginning, we just have to download the results. The interesting thing happens is what happens when I want to join a local table against a remote table? Then we have these two pipelines that meet where the join happens, and then we basically upload the small data to the cloud, or the smallest piece of information to the cloud, and then we do the join in the cloud. We can do the opposite when the remote table is smaller than the local table. We just download the pieces that we need. So, we can build sort of a robust system that does this. But I think you may ask, well, so why would I care about this? Why does anybody need to do this? And there's some kind of cool things you can start to do once you have this sort of full-blown hybrid execution mechanism. And so these are things that are sort of future work. But once you have kind of the ability to take your database and split it into pieces and have it locally and remotely, there's other stuff that's possible. Well, you can also, for example, you can do really fast scans. You can actually farm things out to multiple machines, and they can do the execution in parallel. One interesting thing about this is if you kind of turn this sideways, this looks like just the same architecture as a typical distributed query engine, where you have an aggregator, which is now the client, and the servers, which are the leaf nodes. So anything you can kind of do in a more traditional parallel distributed system, distributed query engine, we can do using the same mechanism. Other interesting things, if you can do two, if you can do local and remote, basically you can do N. So one way of thinking about it is I could have data that's query engine locally. I could have a local edge cache. that pulls data locally, and then I can have the kind of the main centralized data warehouse, and this will let actually people start to disaggregate their data warehouses so that you don't have to actually have all of the data at the same place at one time, which actually is super expensive. Another one is cross-region joins. So the same mechanism can just let you the same mechanism that can let you kind of join local versus remote lets you join actually two things that are in different regions. So you don't have to necessarily worry about where does your data live, and we can sort of optimally move data as needed. And then the other one is sort of, I call it reversing the polarity, which is instead of clients querying up to the server, is you could actually have an admin query data that lives on the clients. Basically, those same connections just can be reversed, and so you can actually query over data that lives on your local machine. So let's say you're collecting data on around the world. Instead of having to aggregate that all to this central location, you could actually just sort of query. You could leave that data where it's being generated. In conclusion, architecture matters, abstractions matter, and I just hope maybe got you to think a little bit about kind of what do you think is the architecture that's going to get us to the next phase in the data journey. Thank you very much. Yes, I'm happy to answer the question. I think we don't have a whole lot of time left. I think we have 2 seconds, but also I'll be at the MotherDuck booth all the rest of today and tomorrow, and happy to answer any questions that people have.
Yeah, I was wondering, what do you think would be the first gateway application for MotherDuck?
Sorry, the first what kind of application?
Gateway application.
Gateway application. I think if somebody is building an application that they need to expose data to their end users, being able to do this, hybrid execution thing where you can actually run and push workloads down into the browser is really super powerful. We're seeing a bunch of people already that are doing that. Thanks.